This is the history of the atom. This is a scientific method where you make a theory, adjust it, fix it, go on, test it, adjust it, fix it, and keep on going. The very first group of people that had enough time on their hands were the ancient Greeks to study systematically nature. Everybody else up to this time were really working hard just to survive. The unique combination here was the ancient Greeks who were rich merchants. Rich being important because they had spare time on their hands, and they had spare time on their hands, so they didn't have anything else to do but talk about philosophy and such. Merchants, they were exposed to other societies, and so they weren't locked in on one idea. They were able to argue other ideas. They did no experiments because that was below their social stature. If they did experiments, they were laborers, or worse yet, slaves. And they used logic only. What they said was they observed and talked about things like a green stick burning would first give off sap or water, then it would start to smoke or air, and then catch on fire, and then you'd be left with the ashes or earth. So they said that the elements were earth, air, fire, and water. Aristotle was the one that put them in that order, opposites to each other. And so he said there were four elements of the earth and one of the heavens, which he called ether, the sun, the moon, stars. Aristotle was not a merchant. He was in the second grouping of people. He was a professional educator. He educated Alexander the Great. So he was did that. A lot of his writing survived. He was right on a lot of stuff, or on the right track on a lot of stuff. He also, because people stubbornly believed in whatever Aristotle said must be true, set science back for 2,000 years because people didn't want to go against what Aristotle had said. One of the things he said was matter was continuous. If you had a sharp enough knife, you could take a stick and cut it in half forever and ever and ever, like fractions, 1/2, 1/4, 1/8, and so on and so on. The atomists were the fringe minorities, Sasquatch believers, wacko people. They believed in tiny bits of matter. Matter exists in tiny bits, and they called them atomos, which we call atoms now. There was only two on record, Democritus and Leopoldus. And they were really big, Greeks were really big into geometry. So the element earth, since it's sturdy and solid, must be like a brick, because bricks are sturdy and solid. Air, you can move your hand through air easily, so it must be a very small sphere. Water, you move your hand through, but not as easy, so therefore it must be a larger sphere. And if you put your finger in fire, it hurts, so fire must be made up of lots of points. That led to the Romans, who didn't do a whole lot. They were great engineers but not scientists. And the Middle Ages, the alchemists. The alchemists were sort of the anti-ancient Greeks because they did lots of experiments, but very little math and/or logic. Their logic definitely was on the weak side. two things they were after: elixir of life, anything that elixir of life, something that made you drink, you would live forever, and the Philosopher's Stone. The Philosopher's Stone was something that could transform elements. Elixir of life, basically the things they said was anything that rose towards the heavens was holy, things that fell were bad. So anything that rises is holy. So they did some experiments with alcohol, which was necessary for life as a disinfectant of their drinking water. So what they did was they collected the vapors of water, and they were one of the first ones to come up with strong alcohol. And they would mix these with herbs and roots and plants because they were looking for something that would make you live forever. And they came up with medicines. They mixed it with seaweed to get tincture of iodine, which is the first antiseptic. They mixed it with certain roots and herbs, like maybe mixing it with willow bark, which would make aspirin. They would also mix flowers with it, which would be the first purpose of the perfume. They made perfume for the first time, which is important because people did not believe in bathing. On the Philosopher's Stone, they believed in mixing male and female elements. They thought sulfur was particularly male, yellow, dull, fiery, stinky. Female, they thought was mercury, pretty quick, pretty shiny, changes its mind, so it's quick silver. And when they mix those two elements together, they sometimes got some yellow substance, which they thought looked like gold. So they thought they could grow or meld male and female substances. Onto the modern scientists, they continued the benefit of experiments, but they did measurements. They were big into measurements and recording things. Their technology improved so that they could record things with grams or mass and time, for like Galileo when he did his clock, the falling objects, and to which they started doing some more math. One of the first early chemists was Lavoisier. Lavoisier was a Frenchman who came up with the first concept law of conservation of matter. He did experiments in a closed system, which allowed him to get good results, and he had good measurements. He also wrote the first chemistry textbook, but he was also a tax collector at the time of the French Revolution, so he was not looked favorably upon, and he was beheaded. Also close to this time was the law of constant composition, where no matter what the substance was, no matter where it came, it had the same percent of the elements. Like salt was always 23% sodium, no matter where it was found. Which is important for John Dalton. John Dalton was an English high school teacher. They taught all sorts of subjects, ancient Greek, science, everything else, history, everything. He was familiar with the atomists and the science that was coming around him, and he had several postulates or things that made up his theory. First, the modern atomic theory. Matter is made of atoms, which he stole directly from the atomists. He said that atoms cannot be created nor destroyed. And this explains Lavoisier's conservation of matter. If matter is made up of atoms and matter cannot be destroyed, therefore atoms cannot be destroyed. He said that atoms of the same element are identical, and he thought it was identical by mass. Atoms of different elements are different. Again, he thought proposed by mass. Atoms combine in whole number ratios to make compounds, which explained the law of constant composition, because it had one atom to one atom, and one atom was 23% of sodium chloride. Then the sodium atom, if the sodium atom was 23% of the compound, then the compound would be 23% sodium. So that makes sense to them. He did make a mistake. He did not know about diatomic elements, which messed things up for a long time. And he thought things would exist in simplest whole number ratios, which is 1 to 1. So he thought that water was HO, one hydrogen, one oxygen, because that was the simplest combination. He was wrong. Dalton's model of the atom. He said the atom was solid, spherical, like a pool ball, solid, no internal structure. So that was his model. People were studying at this time something called a Crookes tube, which is passing electricity through an empty tube, and Englishman called J.J. Thomson came up with an experiment. What he did was he hooked up a metal to a negative battery pulse and a little washer type thing to the positive battery post. The electron, or the negative part of the cathode rays, would zoom this way until one of them would hit the hole and hit a screen on the opposite side here. So it would come through and hit the screen and make a little dot. Then what he did was he studied the composition of that by putting a cross current and turning it on, and it bent towards the positive, which means it was a negatively charged object, and he could calculate the slope. That slope he could calculate, and it was dependent upon two things: the charge of whatever this particle was divided by the mass of whatever this particle was. And he had no idea. There's three variables, but he only had one number, and he couldn't find the other ones. So it was left up to an Englishman, or an American in Chicago, University of Chicago, called Millikan, and he did what I call the oil drop experiment. What he did was he put two metal plates, charged one positive, charged one negative, and squirted some oil droplets. And he made them, so the oil droplet, he zapped them with like a bug zapper, so they had some charge on it. And some of it would fall down by gravity, but if they were negatively charged, they would also be attracted up. And what they did was they adjusted a rheostat to make it hover. You knew the force of gravity pulling down, you knew the force of electricity pulling up, and you could find what the charge was on this oil drop. The problem is he didn't know if it was one charge or 5,000 charges. So what he did was he set up a set of experiments, and he did it thousands and thousands of times, and he noticed that they would group up. There would be a whole bunch at some numbers and a lot less at others. The minimum gap was, the smallest gap in charge was the charge of one of these particles. So he found the charge of one of these particles, and J.J. Thomson said, yay, 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 I found it. And it was roughly 1/2000th of the size of hydrogen. Now, hydrogen's the lightest element, and Dalton said atoms are the smallest particle possible, but if hydrogen's the smallest element, how can something be smaller than the smallest particle? So what J.J. Thomson found was that first subatomic particle. He did more experiments, he reversed this field, and he found out another thing that had a positive charge, but was much, much heavier, and it was 1999th out of 2000th of the hydrogen particle. And he called this thing a proton, and the other thing he called an electron. So we came up with something we call the chocolate chip model. Chip cookie model. It was like a chocolate chip. The proton would be like the dough, and the electrons on the inside were like the chips, because most of the mass was proton. Most of the mass of a cookie dough is chocolate chip cookie is the dough. Now, he didn't say chocolate chip cookie, he said plum pudding, but people don't know what plum pudding is. This led up to a experiment by Geiger. Geiger worked for a guy named Rutherford, and this is the guy that did the Geiger counter. And what he did was he had some uranium ore that shot off some of these alpha particles, which had a positive 2 charge. And he shot them at a very, very, very thin gold foil that was about 3 atoms thick. Now, theoretically, they should all zap through there really quickly, and most of them would go there, and very few would go a little bit deflection. What they're trying to figure out is back over here, if you were going to get close to the proton, how much would it move over? If you could get closer, how spread out were the electrons inside that chocolate chip cookie? So they were expecting very small deviations from straight through, and did the experiment. 99.999% did go straight through. And once in a while they found one that went that way. And to their shock and dismay, every once in a while one would bounce back. He said this was like shooting a machine gun through tissue paper and having one of the bullets ricochet back and hit you in the head. You'd be very surprised and very dead. We call this the shooting gallery experiment. This led Rutherford to come up with his model of the atom, where the nucleus contained the protons and orbiting that were electrons around it. This is the solar system model, where the nucleus is like the sun with most of the mass in the middle, and very little mass, like the electrons, being the planets orbiting around. The problem with this does not explain why certain elements gave off certain colors, like yellow, green, red, like in fireworks. So a Danish scientist named Bohr came up with his model, and he kind of worked backwards. He said, well, if this gives off this color light, what needs to be happening for the electrons to do that? And he said that in order for certain colors of light to be given off, you must have the electrons orbiting around the nucleus, which now contain protons and neutrons, because that was found out, in set orbits. This is the only way of doing that because the energy going from one orbit to another gave off set color. This I call the boring model. Catchy, eh? That comes up to the modern model of the atom, which has not changed appreciably except for quarks, and chemists are only involved or concerned about electrons, mostly anyway. Where the electron is no longer a particle. The problem with the Bohr model is eventually these negative electron particles would decay going to the nucleus, and, well, we're still here, so that doesn't happen. So what we said was the electron is a wave, which works out that one orbit happens to be one wavelength. The next orbit would be two wavelengths, and on and on. So the electron can be a wave if it's surrounding the electron, or surrounding the atom. But if it's going down the wire to your TV screen or something, it's not a wave, it's a particle. So one of my students called this a wavicle. I've stolen it ever since. So the modern model of the atom has the electron being a wavicle, where it can be a wave and a particle both. And this is called the wave-particle duality of nature. So the final model we have is the nucleus, where the protons and neutrons exist. And surrounding that is a cloud of possible electron locations. Now, if the electron's a wave, where's the wave? Where's the light in the room? Well, light is everywhere. So where's the electron? It's everywhere in here. It's not just a bunch of dots, each one representing an electron. It is a possible location of it. It's like showing a flashlight. It's brighter in certain areas, but if you go outside the beam of the flashlight, it's dimmer. So the electron fills the space. It's not just there. That ends this long lesson on history of the atom.